Hey guys, today we're going to talk about Chapter 11, square root functions. Alright, so a square root function, a square root function is a function whose rule contains the variable under the square root sign. Okay, so for example, if I have f of x equals the square root of x minus 3 plus 5, this is a square root function, okay, because there's a square root inside it. Notice there's not an x on the outside, okay, it's just x is on the inside, so this is a square root function. So the function y equals 8 square root of x gives the speed in feet per second of an object in a free fall after falling x feet. So we're going to find the speed of an object in a free fall after it has fallen 16 feet. So this means that if x is how many feet it's fallen, then we've got x equals 16, so I'm going to find out what y equals. Y equals 8 times the square root of 16, which we know the square root of 16 is 4. So that means y equals 32 feet per second. So feet per second. Okay? FPS. Okay, well next we're going to find the speed of an object in free fall after it has fallen 20 feet. So that means x equals 20, and I'm going to do y equals 8 square root of 20, but we don't know what the square root of 20 is, and since it says to give a decimal because it says nearest tenth, I'm going to go to my calculator and I'm going to type in 8 times the square root, that's right, control and the little square root button, 20, and I'm going to press control enter, and that'll give me the decimal. Another way to do that is 8 square root of 20, and you can put a decimal, you can put a decimal right after that, and it'll think it's a decimal, so then it'll give you the decimal. Alright, so 37.8 feet. So it says nearest tenth, so we're going to say equals 37.8 feet per second. Okay? Okay, note, when dealing with real numbers, 35.8, I'm sorry. Alright, there we go. Alright, so note, when dealing with real numbers, you can never take the square root of a negative number. This means that when you're dealing with a square root function, our x values are restricted, which means that our domain changes. Okay, remember we talked about domain earlier this year. Domain is the values of x that are able to be used in the function. So let's see what this does, okay? Square roots, the stuff inside a square root cannot be negative, so this stuff right here can't be negative. So in order to find the domain, I'm going to say, okay, x minus 4 has to be greater than or equal to 0. And then I'm going to solve for x. So I'm going to add 4 to both sides, and that gives me x has to be greater than or equal to 4. So there's my domain. I'm going to go ahead and write it in set notation. This is going to be an interval notation, I'm sorry. So this is smallest value is 4 and anything bigger than that. So there's my interval notation, including 4 but not including infinity. And this is my domain. Alright, let's try this one. Well, I've got 4x plus 3 has to be greater than or equal to 0 because the stuff inside can't be negative. So first I'm going to go ahead and divide both sides by 4 because that's what's on the outside. So I have x plus 3 has to be greater than or equal to 0. Now I'm going to subtract 3, and I've got x is greater than or equal to negative 3. So my domain is negative 3 to infinity, and include negative 3. Okay? Alright. Now remember, when you divide by a negative, let's say this was the square root of negative 4x plus 3. When I divide by negative, that would switch the sign. So it would be negative 4x plus 3 is greater than or equal to 0. Divide by negative, I get x plus 3 is less than or equal to 0. And then I would get x is less than or equal to negative 3. Okay, so you have to be careful about those negatives. Okay, now go to your warm-up and complete problem number 1. Okay, the parent function for the square root function is f of x equals square root of x. All right, this is the parent function. So we're going to graph this. Well, what numbers have nice square roots? Okay, x and f of x. Well, when x is 0, we know that the square root of 0 is 0, so I'm going to plot that point. When x is 1, we have a nice square root of 1, so 1, 1. 2 doesn't have a nice square root, 3 doesn't have a nice square root, 4 has a nice square root, and that's 2. So 1, 2, 3, 4, up 2. Okay, we have to look for the pretty square roots for x. Another one, the next one's going to be 9, and that has a square root of 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9, up 3. And then one of the square root's going to be 4, as you can see this pattern, and that would be 16. Well, that's not on our graph. I mean, I didn't give us that many slots, so I'm just going to graph it from here. Notice if I put a negative in, it's going to not give me an answer. So this is actually the whole graph. It starts at 0. And it goes that way. It does not go that way. So we don't put an arrow on this side. So this is my square root function, the parent function. Now we're going to graph the curves of f of x equals the square root of x plus 1, the square root of x plus 3, and the square root of x plus 5. Well, what are these numbers doing here? Well, if you can see, this plus 1 is happening after I take the square root. So I'm adding 1 to all of the vertical values. This is a vertical shift. Okay, this is a vertical shift. So it's going to go, this one's going to go up 1, this one's going to go up 3, and this one's going to go up 5, okay, from the parent function. So if I want to graph this guy right here, I'm going to take this value and shift it up 1. Okay, this value shifted up 1. This value shifted up 1. This value shifted up 1. And then I'm going to graph the points. Graph my curve. There we go. Okay, so that's that curve. The next one, let's see, different color. How about this one? All right, plus 3. So I'm going to take my parent function, I'm going to add 3. 1, 2, 3. So right there, parent function 1, 2, 3. Parent function up 3. Parent function up 3. And then I'm going to graph it. Okay? And this one, I'm going to take the parent function and I'm going to go up 5. So 1, 2, 3, 4, 5. I'm going to go to the parent function and go up 5. 1, 2, 3, 4, 5. Up 5. Up 5. There we go. Okay, there we go. Those are our different functions that we've got down there. So what we're really doing here is we're translating the parent function. So the graph of f of x equals the square root of x plus k is a vertical translation of the graph of f of x equals square root of x. Okay? And if we're looking at the graph of f of x equals the square root of x minus h, is a horizontal translation of the graph of f of x equals the square root of x. Okay, so let's look at the general equation here. If we have the general equation of a square root function is f of x equals a square root of x minus h plus k. All right, that's as much as we're going to do in Algebra 1. And let's look at what each of these things does. This is a horizontal shift. Okay? This is very much like vertex form, okay, in the quadratics. So the negative h is going to move, the h is going to, this form, if it's minus, is going to move to the right, and if it's positive, it's going to move to the left, because h is going to be which way we're moving, okay? And the plus k is the vertical shift. Okay, and that's up or down. and A is your compression, your stretch. Okay, so normally we have the relationship of over 1 up 1 over 4 up 2 over 3 up 9. Okay, this is going to multiply your vertical values over 9 up 3, I'm sorry. This is going to multiply your vertical values by a constant. So let's see what that means when we get there. So let's graph these curves. Here we have horizontal translations. Okay, so here I'm going to move to the right 1, I'm going to move to the left 2, and I'm going to move this one to the right 4. Okay, so first I'm going to graph my parent function so you can see what I'm graphing. Here's 1, 1, or 0, 0, 1, 1, 4, 1, 2, 3, 4, 2, 9, 4, 5, 6, 7, 8, 9, 3. Okay, so this is my parent function. If I can, there we go. Okay, and I'm going to graph this first one in green so you can see it. I'm going to shift it to the right 1. So each of these points is going to be shifted to the right 1. Notice I still go over 1 up 1, over 3, or over 4, up 2, over 9, up 3, and there we go. There we go. Okay. The next one I'm going to graph, let me graph it in a different color. How about this one? Alright, is going to be a left shift 2, so I'm going to start down here, over 1 up 1, over 4, 1, 2, 3, 4 up 2, over 9, 4, 5, 6, 7, 8, 9 up 3, and I could probably go over 16, but I'm just going to stop here. Okay, and then the last one, if I can get a good color, here we go. I'm going to shift it to the right 4. So here's my parent function, 1, 2, 3, 4. So there's my first point, over 1 up 1, over 4 up 2, 5, 6, 7, 8, 9 up 3. You're probably saying to yourself, man, they get really close together. Well, yeah, of course they do. This is like a parabola kind of cut in half and sideways. Okay? Alright, so we're going to graph the square root function. Well, here, all we have is one translation. We're going to go to the right 3. So my parent function starts at 0, 0. I'm going to start at 3, 0. Okay? I'm going to go over 1 up 1. If I wanted to, what I could do here is I could say, okay, well, that's all fine and dandy, Mrs. Meller, but how do you know it goes over 1 up 1? Well, if I make a table and I plug in 3, 3 minus 3 is 0, so that's the square root of 0, which is 0. If I plug in 4 here, I would get 4 minus 3, which is square root of 1, so that's 1. And the next one I would want is going to have to be a 2 here. So when does x minus 3 equal 2? Well, when x equals 5. Oh, I want square root of this equals 2. So that means I would need it to, let's see, equals 2. So that when I square both sides, I get x minus 3 equals 4, so x equals 7. So that's going to be 7, 2. From, that's the point 7, 2. 1, 2, 3, 4, 5, 6, 7, up 2. So I like to think of it as over 4 from the point, from the initial point, okay, to over 4 up 2 because it's easier to do that. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, up 3, and there we go. These are much easier to graph with translations than with plotting points because of the fact that you have very few lattice points that are easy to graph. Okay, so here's another one. Okay, this one says that we take the square root function, we're going to shift it up 4, and we're going to multiply the vertical difference by 3. Okay, so it's a vertical stretch by a factor of 3. So first I'm going to go ahead and I'm going to shift it up 4. 1, 2, 3, 4. Okay? Now, if you remember, okay, my parent function did this. At x is 0, you had 0. At x is 1, you had 1. When x is 4, you had 2. When x was 9, you had 3. Okay? Well, I'm going to add f of x plus 4, and that's going to give me, well, that's going to give me what I've got here, okay? But do you see how the height between here and here is 1? I'm going to multiply that times 3 to get 3. So instead of going over 1 up 1, I'm going to go over 1 up 3. Okay? So here, I'm going to multiply this times 3. So instead of going over 4 up 2, I'm going to go over 4 up 4. So over 1, 2, 3, 4, up 1, 2, 3, 4. Oops, over 4 up 6, I'm sorry. It's really early, guys. I'm really kind of half asleep. Okay, so over 4 up 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. There we go. All right, so now do you see how it's a lot steeper? This square root function is a lot steeper because we multiplied all of the vertical values by 3. I'm going to draw the parent function once more. So you can see where we got these, okay? So normally it goes over 1 up 1. This one went over 1 up 3. Okay? Then it goes over 4 up 2. Well, this one went over 4 up 6. Okay? So this was 2 and this is 1. Alright, so there's where our multiplying is coming in. I hope that helped. Okay, so now go to your warm-up and complete problem number 2. Alright, so we've kind of already touched on this a couple of times, so we're going to go over it once more so we get it all nailed down. A radical expression is an expression that contains a radical. Okay? A radicand is the stuff under the radical sign. So here's a picture of what we've got. This right here, this little sign right here is called the radical. Okay? This thing right here is called the index. Right now we're using an index of 2, and when indexes of 2 occur, then you really don't have an n. So if I have the square root thing, it's an understood index of 2. Okay? This stuff under here is called the radicand. And the whole thing together we call a radical expression. Okay. So the product property of square roots. For any numbers a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, the square root of a product is equal to the product of each square root. Okay, so for example, the square root of AB equals the square root of A times the square root of B. Now this works both ways. If I have this, I can multiply them together. Okay, now this is only if the index is the same, but we're only dealing with square roots today, so this is going to be fine. So let's simplify this. Well, I know that 12 is 4 times 3. And 4 has a nice square root. So the square root of 12 equals the square root of 4 times the square root of 3. Well, what's the square root of 4? Well, that's 2. And so that's 2 times the square root of 3. Now, last time, a couple of times ago when we were simplifying square roots, I told you guys, look for the twins. Okay? That's exactly what we're doing here. Okay? The twins come out, they sit in front. See, there you go. Okay? Here's another one. we know that that 90 is 9 times 10. 9 has a square root, so that equals the square root of 9 times the square root of 10. The square root of 9 is 3, and the square root of 10 does not have a nice simplification because that's just 5 times 2. So that would be our simplified answer. Okay, so we've looked at it two different ways of simplifying. We've looked at look for the twins, which are right there. They come and sit out, and what's left over is the stuff that makes up 10. Okay, 52 may not be as obvious. All right, I know that 2 and 26 2 and 26 make up 52, and then I have 2 and 13. This is the situation where I would probably just do the twin thing, but 2 times 2 is 4, so this equals the square root of 4 times the square root of 13, which equals 2 times the square root of 13. And this one, 7 is 9 times 8, and 8 is 4 times 2. So this one we could actually break up 3 times. The square root of 9 times the square root of 4 times the square root of 2. Well, the square root of 9 is 3, the square root of 4 is 2, and the square root of 2 is the square root of 2. So we have 6 square roots of 2 as our final answer. If you were looking at it from the perspective of the twins, we could break down 9 and break down 4 into 2 2's. There's a set of twins and there's a set of twins. They multiply together and sit in front, and the one left over is this 2 right here. So go to your warm-up and complete problem number 3. Okay, so let's find this expression. Well, 24 is the same thing as 4 times 6. So this equals the square root of 2 times the square root of 4 times the square root of 6. And the square root of 4 is 2, so we can go ahead and find that one. And the square root of 2 times the square root of 6 is the square root of 12. Okay, but 12 also has a 4 inside it. So this is now 2 times 2 square root of 3, which equals 4 square roots of 3. And you probably said, Mrs. Meller, that was really confusing. Is there any other way we could have done that? And I say, of course there is. This is probably how I would have thought of it to begin with. The square root of 2 just has the factors of 2 inside it. And then I'm going to multiply that by 24. And 24 is 8 times 3. And 8 is 4 times 2. And 4 is 2 times 2. So we have one set of twins. And then this one pairs up with this one for another set of twins. And they come out. So that's 4 square roots of 3. And I'm done, because he's the only one left on the inside. Now notice 8 has been broken apart, so we don't look at him anymore, and 4 has been broken apart, and 24 has been broken apart. So the only ones we look at are 2, 2, 2, 2, and 3. So go to your warm-up and complete problem number 4. Okay, so here's one with a lot of stuff under the radical. Well, I'm going to do the twin thing so it makes a little more sense to those of us who think that way. This is 9 times 5, and this is 3 times 3. So here's a set of twins that's going to go out. Okay, so I'm going to go ahead and start making my new house. 3 comes out, 5 stays inside. Now let's look at the a's. Well, a to the 4th is a times a times a times a, which has 2 sets of twins, so a squared comes out. Okay, another way we can think about it is this is a radical with an index, like with an index of 2, so this is 4 divided by 2 is a squared, right? B to the 5 is b to the 1/2, b times b times b times b times b. So here's 1, and there's the leftover, so leftover comes in here. B squared stays out here. C, 1, 2, 3, 4, 5, 6. 1 set, 2 sets, 3 sets outside. So we have 3a squared, b squared, c cubed, square root of 5b. And that's our final answer. Okay. So now go to your warm-up and complete problem number 5. The quotient property of square roots. For any numbers a and b, where a is greater than or equal to 0 and b is greater than 0, the square root of a quotient is equal to the quotient of each square root. So, for example, the square root of, so, for example, if I have a over b, this equals the square root of a over the square root of b. Okay? So there we go. So rationalizing the denominator, getting the square root out of the denominator is what rationalizing is called. Because you're not allowed to have a square root in the denominator. Well, first, multiply the top and the bottom by the square root that's in the bottom. Okay? So here's how we're going to do this. Notice I have the square root of 10 over the square root of 3. So I'm going to multiply by the square root of 3 over the square root of 3. And that gives me the square root of 30 over 3. Now, the square root of 30 is not reducible because it's just 2 times 3 times 5. So there's no twins in that one. Here, I'm going to multiply by the square root of 5 over the square root of 5. Well, 12 times 5 is 60. Okay, and 60 does have twins inside. That's 6 and 10, 2 and 5, 2 and 3, so the 2's come out. Okay, so we have 2 square root of 15 over 5, and we're done with that one. Okay, let's look at this one. I'm going to multiply, well, first of all, 27 can be simplified, so we're going to do that really fast. Square root of 11y over 27 is 9 times 3, and that's 3 times 3. So this is 3 square root of 3. So I'm going to multiply the top by the square root of 3 and the bottom by the square root of 3 so that I can get the square root out of the denominator. So now I have the square root of 33y over 3 times 3, which is the square root of 33y over 9. And I'm done with that one. Okay, this one, again, 8 can be simplified, so let's go ahead and simplify it. The square root of 3 over, okay, 8 is 4 times 2, and 4 is 2 times 2, so 2's can come out. We have 2 square root of 2. So I'm going to multiply the top by the square root of 2 and the bottom by the square root of 2. And that gives me square root of 6 over 2 times 2, which is the square root of 6 over 4. And we're done with that one. Okay? So notice I just remember square root of 2 times the square root of 2 is the square root of 4, which is 2. So that's why the square root goes away. So now get to your warm-up and complete problem number 6. So in summary, a radical expression is simplified when these are true. No radicands have fractions. No radicands contain exponents. Okay, and no radicals appear in the denominator of fractions. Now, this means for square roots, okay? You could possibly have an exponent if it's a greater than a square root. So what do you do next? Go to Edmodo and answer the following question. How do you simplify a square root? And then if you have a question, please ask me, and bring your notes and cool down to class and warm up. All right, see you guys later. Bye.